In the previous lecture, we have discussed about the critical section problem, and we saw why the critical section problem is important. And we have also seen what are the requirements that a solution to the critical section problem must have. So in this lecture, we are going to discuss a software-based solution to the critical section problem, which is known as the Peterson's solution. Before we go into the algorithm of Peterson's solution, let us understand a few points about Peterson's solution. So this Peterson solution is a classic software-based solution to the critical section problem. So as I had just said, it is a software-based solution to the critical section problem. And also, this Peterson solution may not work correctly on modern computer architectures. So because of the way modern computer architectures are designed, this Peterson solution may not work correctly on these modern computer architectures. But however, it provides a good algorithmic description of solving the critical section problem and illustrates some of the complexities involved in designing software that addresses the requirements of mutual exclusion, progress, and bounded weighting requirements. So you may ask, if this does not work well on modern computer architecture, then why study this? So why we are studying this is because this is a classical software-based solution to the critical section problem, and it will provide us a good algorithmic description of solving the critical section problem, and it will help us understand how to solve this critical section problem at a software level if we are designing a software that needs to have a solution to the critical section problem. And we also saw in the previous lecture that these are the main requirements that a solution to the critical section problem must have: the mutual exclusion, progress, and bounded weighting. So we will see that on a software level, how can we achieve these three requirements as a solution to the critical section problem. So that is why Peterson's solution is an important topic in operating system as far as process synchronization is concerned. Alright, now let's try to understand how this Peterson solution works, what is the algorithm, and how is this a solution to the critical section problem. So this Peterson solution is restricted to two processes that alternate execution between their critical sections and remainder sections. So for understanding, let us call the processes Pi and Pj. So these are the two processes that we are going to discuss about in this Peterson's solution. And also, Peterson's solution requires two data items to be shared between these two processes. So we have processes Pi and Pj, and there need to be two data items that needs to be shared between processes Pi and Pj. And what are they? They are turn and flag variables. So let's see what they are. So the integer turn is a variable that indicates whose turn it is to enter its critical section. So the turn variable will indicate whose turn is it to enter its critical section. So that means if turn equals to I, that means it is process Pi's turn to enter its critical section. And if turn is equal to j, that means it is the turn of process Pj to enter its critical section. So that is the use of the turn variable that we have. So this turn variable is shared between processes Pi and Pj and can be modified by both processes Pi and Pj. Now the next data item that we have is a Boolean variable called flag. So if you see here, flag is actually an array which can store two variables, and it's a Boolean variable. So Boolean means it can have only two values, which may be true or false. So what is this flag? It is used to indicate if a process is ready to enter its critical section. So when the flag variable is set to either I or j, it will indicate if these processes are ready to enter its critical section. So for example, flag of I, let's say we are talking about P of I, and if flag of I is equal to true, that means the process Pi is ready to enter in its critical section. And if flag of j, that means we are talking about process Pj, equal to true. If flag of j equal to true, that means process Pj is ready to enter its critical section. So this flag variable is used to indicate if a process is ready to enter its critical section. So if the value is true, that means that particular process is ready to enter its critical section, and the turn variable will indicate whose turn is it to enter its critical section at that particular time. So these are the two data items that are going to be shared between the two processes that we are going to discuss in Peterson's solution. Alright, now we can go to the algorithm of Peterson's solution. So before we go into the algorithm, let me give you a brief idea of how this Peterson solution works. So in this Peterson solution, when a process wants to enter its critical section, it will set its flag equal to true. So let's say Pi wants to enter its critical section, then it will set flag of I equal to true, indicating that process Pi is ready to enter the critical section. Alright, so that's what happened in the flag variable. Now what about turn? So when Pi wants to enter its critical section, what it will do is, it will set the turn variable equal to the other process. That means it will set turn equal to j. Now you may be thinking, why did this happen? So this is how Peterson's solution works. It is like a humble algorithm. So why am I calling it a humble algorithm? I'm calling it a humble algorithm because when one process wants to enter its critical section, what is it doing? Instead of entering the critical section, it is giving the turn to another process. So that is why I called it a humble algorithm. So let's say that, for example, you and your friend, you are going somewhere and you want to board a bus. So you both reach the bus station and the bus is there in front of you and both of you are going to enter the bus. So you know that only one person can enter the bus at one time through the door of the bus. So what do? So you go there and both of you wants to enter through the door of the bus, and what do you say? You say to your friend, alright, you enter first and after that I'll come. So your friend first enters the bus and while he is entering through the door, you wait, and once he enters the bus, then you enter. So you are giving chance to your friend. You are being humble. So Peterson's solution is something like that. The process, even though it wants to enter this critical section, it is humble and it gives the turn to the other process if that process also wants to enter its critical section. So I am using these terms humble and humility because I want you to understand how Peterson's solution work. So we will now take the algorithm which will make it clearer. Let's see. So here we will be seeing the structure of the process Pi in Peterson's solution. So we have processes Pi and Pj. So we are discussing about these two processes, and let's see the structure of process Pi. So this is the code. So you need to have a basic understanding of how the code works. So let's see. So here we have a do while loop and all the executions are happening within this do while loop. Alright, so let's see. So let's say that process Pi wants to enter its critical section. So what will it do? It will set the flag of I equal to true. We saw that flag is used to indicate if a process is ready to enter its critical section. So flag of I equal to true means process Pi is ready to enter its critical section and wants to enter the critical section. Then what does it do? It sets turn equal to j. So I told you it's a humble algorithm. So even though it wants to enter the critical section, it is setting the turn equal to j. That means it is saying that if process Pj wants to enter its critical section, let it enter first. I will wait. So that is what it says. Now here we have a while loop which says that flag of j and turn equal to j, and there is a semicolon here. So what does this mean? This is the most important part of the Peterson solution. So here we have a while loop, and inside this while we are having a condition. So the condition is flag of j. That means if flag of j is true, and also if turn equal to j, and then these two statements are joined by a AND operation. So when does an AND operation become true? An AND operation becomes true only when both the conditions are true. So only when this and this are both true, then this whole while will be true. So if either one of them are false, then this whole while will be false. That is how AND operation works. And also see that there is a semicolon here. So what does this semicolon mean? So in a while loop, if we are having a semicolon just after the condition, that means this while loop does not have any statements under this. It is only having the condition, and as long as this condition is true, the control remains in this while loop and it will keep on looping inside this while loop and it will not exit from this while loop. So only when this condition becomes false, only then the control will break from this while loop and will come to the next statement, which is the critical section. So keep in mind that as long as this condition is true, it will never go to the critical section, but it will remain in this while loop. Alright, so let's try to analyze this again. So I is equal to true. Flag of I is equal to true. That means I wants to enter this critical section. So what does it do? It is being humble and setting the turn value equal to j. That means if j wants to enter this critical section, let it enter. Let's say that the process Pj also wants to enter this critical section. So what will that process pj do? It will also set its flag of j equal to true. So flag of j will be true and turn equal to j. So process pi already set the value of turn equal to j. So turn equal to j. So this is also true. Flag of j means process pj wants to enter this critical section, and turn equal to j is set by this process pi over here. So both conditions are true. So when both conditions are true, what happens? This while condition is completely true and it will remain in this while loop and it will not come out of the while loop as long as one of the conditions here becomes false. So if there is a semicolon means it will keep on looping inside here. So if this condition is true, it will never come to the critical section, but it will remain here. So pi is not able to come to its critical section, but it is allowing pj to enter its critical section. Alright, now when one of the condition becomes false, then this whole while will become false, because it's an AND condition, and it will break from this while loop. Then it will be able to enter its critical section and it will execute in its critical section. Then it will set flag of I equal to false because it has completed its critical section, and then the flag of I is set to false because now it does not have to execute in critical section, and then the remainder section will be executed. Alright, so this may be a little bit confusing, but it will become clear when we take the structure of process pj as well. So here we have the structure of process pj, which is almost similar to this except for the variables that are changed. So see here, in process pj, if process pj wants to enter its critical section, it sets its flag equal to true. Alright, and again process pj will be trying to be humble, and what will it try to do? It will set the turn equal to I. It is saying that I want to enter the critical section, but if pi also wants to enter its critical section, let me give the turn to pi. So the turn is set to I. And then similar kind of condition is here. If flag of I is true and turn is equal to I, that means if I wants to enter this critical section and also the turn is equal to I, then what will happen? The control will remain in this loop. So j will not go to the critical section but will be looping over here until and unless one of the condition here becomes false, and then only j will be allowed to enter the critical section, and after it enters it will set flag of j equal to false, and then the remainder section will be executed. Alright, now to understand it further, let's take a live example. So let's say that both processes pi and pj wants to enter the critical section at the same time. Now should that be allowed? That should not be allowed. The critical section problem tells us that no two process should be allowed to enter its critical section at the same time. So only one of them should be allowed to enter the critical section. So let's say process pi and pj are both trying to enter the critical section. So what will happen? Pi will execute this first statement, flag of I equal to true, which says that pi wants to enter this critical section. And pj also sets flag of j equal to true. That means pj is also saying that I also want to enter the critical section. And then what happens? It's Peterson's solution. So pi is going to be humble and it is going to set turn equal to j. So it will say that if j wants to enter this critical section, let the turn go to j. I will wait. And what about process pj? Pj also does the same thing. It is saying that turn equal to I. That means if pi wants to enter in its critical section, let the turn go to I. So what happens here? Turn was set to j by process pi, but after that what happens here? Turn is set to I by process pj. So as I told you, this turn is a shared variable, so it will have only one value and the last set value will be the final value of turn. So here turn was set to j by process pi, but it was also set to I by process pj. So the final value of turn is now I. So keep that in mind. Now let's see which of these while conditions are going to work. So let's see this while condition of process pi. So it says here while flag of j. So what is the value of flag of j? Flag of j is true. Okay, this first condition is true. And turn is equal to j. Now what is the value of turn? Is it j or I? So I told you the final value was I. Process pj has set the turn value as I. So turn's value is not j, but it is I. So this portion is false. So what will happen to this whole while? This is true, but this is false. So there is an AND condition. So AND condition will be true only when both are true. But here since one is false, this whole condition will be false. Now when this whole condition is false, what will happen? This while loop will not hold. it will break from this while loop and it will come to the critical section part. So what will happen? Pi will be executing in its critical section. So when Pi is executing in its critical section, let's see, is Pj also executing in its critical section or not? So if you see here, what is the while condition over here? While flag of I. So what is flag of I? Flag of I is true. We know it is true. And turn equal to I. Is the value of turn equal to I? Yes. I told you that turn's final value was I, which was set by process Pj. So turn is equal to I. This is also true. So flag of I is also true and turn is equal to I. This is also true. So both these conditions are true and there is an AND condition. So that means this whole while is true. So when this whole while is true, see that there is a semicolon here. So it is going to loop in this while condition and it is not going to enter this critical section as long as this while remains true. So we see that when Pi is executing in its critical section, Pj is in this loop and is not coming to the critical section. So only Pi is allowed to enter this critical section. And after Pi completes its critical section, what happens? It is setting the value of flag of I as false, because it has completed its critical section. So it is indicating that I don't want to execute in critical section anymore. So flag of I is set to false. And then it goes on to execute its remainder section. Now at that time, let's see what happens to process Pj. So Pi has completed and it has set flag I equal to false. So here what happens? Flag I becomes false now. So flag I is false and turn is still equal to I. So this is true. And this becomes false now. So when this becomes false and this becomes true, we see that there is an AND condition. So the whole of the while condition becomes false. Because as I told you, AND condition will be true only when both the cases are true. So here one condition becomes false. Hence the whole while becomes false. So it will break off from this while loop and will come to the next statement, which is the critical section. So Pj is now allowed to enter this critical section and it will execute in this critical section. And once it completes, it will also set the flag of j equal to false, stating that P of j has finished executing in its critical section and then it goes to execute in its remainder section. So here we see that how this Petersons solution has managed to allow only one of the process to enter its critical section at the same time. So we see that by following this method, how the critical section problem can be solved. Only one process is allowed to enter its critical section. Now let us see if all the requirements of critical section problem solution are fulfilled or not. So in the previous lecture, we have seen that a solution to the critical section problem must satisfy the following three requirements: mutual exclusion, progress, and bounded waiting. So the Peterson solution is a solution to the critical section problem. So is mutual exclusion preserved? Mutual exclusion states that if Pi is executing in its critical section, then no other process can be executing in their critical section. So we saw that by the help of this while loop in Peterson solution, when one process is executing in its critical section, the other could not enter its critical section at all until and unless the other process have completed and have exited from its critical section. So mutual exclusion is preserved. Now let's see about progress. So progress states that if no process is executing in its critical section and some process wish to enter their critical section, then only those processes that are not executing in the remainder section can participate in the decision on which will enter the critical section next, and the selection cannot be postponed indefinitely. So here also we saw that the processes that were not executing in their remainder sections, Pi and Pj, we saw that at this portion, they were both not executing in remainder sections. They both wanted to enter critical sections, and these two processes are the ones that are allowed to take the decision of who should enter the critical section. Pi was able to modify the turn variable. Pj also was able to modify the turn variable. So both of them were allowed to take the decision of who was going to enter the critical section. And then the final value depended upon the final value of turn. Whoever modified the final value of turn finally decided who was going to enter the critical section. So progress also is fulfilled. And also we saw that this decision of who should enter the critical section was not postponed indefinitely. A decision was taken and then first Pi got the chance, then Pj got the chance. So progress also is fulfilled. And then lastly, the bounded waiting. So it says there exists a bound or a limit on the number of times that other processes are allowed to enter their critical section after a process has made a request to enter its critical section and before that request is granted. So if we see here, we saw that bounded waiting also is fulfilled, because when one process wanted to enter its critical section and has requested the critical section, it was allowed to enter the critical section and was not kept waiting indefinitely. So we saw here Pi and Pj both wanted to enter, both of them sent the request. Then Pi set the turn to j, Pj set the turn to I. So eventually I got the critical section for its execution and I executed, and after I's execution was complete, we see that Pj was still waiting because of this loop, and as soon as I finished execution, Pj also got its chance. So there is no indefinite waiting. As soon as Pi completed, Pj also got. So bounded waiting is also fulfilled. So we see that Peterson's solution is fulfilling all the requirements that should be there for a solution to the critical section problem. So this is how the Peterson solution works. So this is a classical software-based solution to the critical section problem. So if we are designing something on a software level where the critical section problem has to be solved, so this is a classical way in which you can do it. So Peterson solution does have limitations because it is restricted to only 2 processes, and also in the beginning we said that it may not work on modern architecture because of the way it is designed, but it is an important algorithm that you need to keep in mind, because this will help us to understand how we can solve the critical section problem on a software level. So I hope this Peterson solution was clear to you. Thank you for watching and see you in the next one.